Welcome everyone. Today's lecture is about functions. So we've discussed at the beginning of the course the role of functions in our sort of overall story of how calculus is going to be applied. If you'll recall, we discussed the idea that we start with a real-world system, and from a real-world system we build a model, and the model is perhaps expressed in the language of functions. That would be because, for example, the real-world system may be changing in time. So the model, the mathematical model, consists of functions of time that map a time to a quantity that is varying with time. Perhaps it's temperature, pressure, or the population, or some other quantity. And then, as I outlined it at the beginning of the course, the third stage is to solve that model, or to find out which among a range of possible functions describing its behavior actually describe its behavior. Those functions are solutions of differential equations very often. Okay, so for the next part of the course, we're going to develop the language of functions. It'll be a bit dry for this lecture, but you'll see how this gets used, for example, in the discussion of differential equations later in the course. All right. So I think I'm just going to take the contents as read and move on to the formal definition of what a function is. So a function consists of three pieces of data. They are the domain of the function, the codomain of the function, and the actual information of the function. Now, I want to be clear about what each of these are. To start with, the domain of a function, you can think of that as the set of all possible inputs. The codomain is a kind of container or like a container for all possible outputs. Now, there's some distinction between that. When I say container, that means that B, the codomain, needs to contain all things of the form f of A, where A is in capital A, but it may contain more things. We'll come back to that in a moment. But now I want to focus on the third part, which is perhaps the most familiar, the rule. Okay, so as part of a function, you need to specify a way of mapping each element A of the domain to an element f of A of the codomain. And you should read this word rule a bit loosely. I'll come back to this in a moment. So just read this as some kind of perhaps algorithm that allows you to associate to each element A an element f of B. And this notation, f colon A goes to B, encapsulates these three pieces of data. So it has the notation for the function, it has the notation for the domain, the notation for the codomain. And often we draw pictures like these ones that you can see here, where we draw the domain, the codomain, and f is an arrow that maps between them. And as you can see here, we draw a point for an element. Okay. So let's look at some examples. Is g from r to r, given by that formula, a function? Okay, so what you can see over there, that expression with x plus 1 in the numerator and x squared plus 4 in the denominator, that's the rule, right? Here we see specified a domain and a codomain. And the question is, well, are those three pieces of data, the domain, the codomain, and the rule, do they together constitute a function? And I'm going to emphasize now something I'll repeat several times in this lecture. A function is not the rule on its own. You're used to thinking about a function as being f of x equals x squared, right? Just the rule itself. But now we're going to be quite particular about a function being these three things, right? Not just the rule itself. Okay, for this triple to be valid, I have to check that that rule makes sense for every input in the domain. Okay, so can I add 1 to any real number? Yes. Can I square any real number and add 4? Yes. Can I take the ratio? Well, the ratio is well defined as long as x squared plus 4 is not 0, and it is not 0 if x is real. So the answer is yes. Now here you see the same rule, right? There's a change of a letter, but obviously that doesn't mean very much. It's the same rule, but the domain and the codomain have changed. Now there's C in both cases. And now these three pieces of data do not, in fact, form a function. You might be able to see why. So given a complex number z, can I form z plus 1? Yes. Can I form z squared plus 4? Yes. Can I take the ratio? Well, not always, right? Because maybe z squared plus 4 is 0. No. That's when z is in 2i, when it's 2i or minus 2i. And so when it's 0, that rule just doesn't make sense. It's like a little program that you just can't execute, right? So how can we turn it into a function? Well, the easiest way is just to remove that bad input. So we can restrict the domain to be C, remove those two numbers. So we change the first piece of data. We change the domain to this subset. We keep the same codomain. We keep the same rule. And now that's a function. Okay, so let's talk about some examples of functions. Most of the functions you're familiar with are functions from R to R. In that case, or if we're talking about functions from a subset of R to some other subset of R, we can talk about the graph. So the graph is just the set of all pairs consisting of all it's the set of all input-output pairs. Right? A, f of A, and that lives in A cross B. And if A and B are both subsets of R, then we can think about this as sitting inside R cross R, or R2. And then if we draw that set, the set of all pairs of inputs and outputs, we call that the graph. Right? So for example, you're familiar with sine and cosine. Now you notice that I don't write sine with an x down there, right? So usually you're familiar with writing sine x. And it's always a little ambiguous, perhaps, whether that's a number, right? Is x an unknown? And I'm supposed to think about that as the function, which is this thing that could take any input x and return a real number. Or is that, so is that a number, the output of sine x on a particular x, or is that the function itself? It's kind of left ambiguous in the way we write it. And if I just leave off the x, it's meant to be clear this is the name of a function and not its value on anything. So a particularly easy example of a function is a constant function that just has the same output on every possible input. Right? So for example, if I take f of x equals 1 for all x in x, x in R, that's a function. Let's draw its graph. Well, the graph is going to be all pairs where x is a real number and I take 1 as the second value. That's giving me the height. So that's going to be a straight line at height 1. Okay, so that's the graph of f1. f2, well, it's changed to give me output 2, so I should put it at height 2. What's also changed is the codomain is z. Now you notice that I don't really care, right? That's a subset of R, so what I said over there makes sense. I can still sketch its graph. And I'm going to put a point at position x, 2 for all x in R. Here, however, something changed that matters. The domain is now z. The height's now 3, that's fine, but the domain is z. So that means that when I consider the graph of f3, I'm going to take all pairs where x is now only an integer. What that means is that I don't get a line like I did before. Instead, I get a bunch of dots, right? So this is 0, 3, minus 1, 3, minus 2, 3, minus 3, 3, 1, 3, and so on. Okay, and that goes on forever. Now, this is maybe a bit of a strange example, but it's just making the point that functions can take as inputs anything you like, any set. So we could take, for example, the set of all English words and a sort of capital letters, or just letters rather, and take alpha to be the function that returns the first letter in a word. That's a well-defined function. I guess we're not going to graph it though. Okay, so we're going to spend some time now talking about some hopefully familiar functions, various trigonometric functions. And the thing I want you to pay attention to here is the domain of tan. So tan is sine divided by cosine. That's familiar. Which means that it's only defined on real numbers where cosine is non-zero. Of course, sine and cosine are defined everywhere. And the numbers where cosine are non-zero, well, cosine is 0 at pi on 2, and anything that differs from pi on 2 by a multiple of pi. And that's what that says, right? If you expand that out, it's pi on 2 plus 2k pi on 2, or what's the same, pi on 2 plus k pi for any k. All right, so you see here the utility of some of the set theoretic notation, the backslash for the complement, and this descriptive set notation. It's a way of saying what the domain of this function is. It's still maybe not exactly clear to you why we need to be so fussy about that and worry about saying the domain precisely, but we'll come back to that a little bit later. All right, so we're going to move over here to the next set of boards. Okay, welcome. So you're familiar with this terminology. Cosecant is 1 over sine. Cotangent is cosine on sine. Here's a little bit of an interesting wrinkle, right? So I could have defined this a little bit differently. So I could define the cotangent to be 1 over tan. That would be consistent with cosecant being 1 over sine. So what's the difference between this and this? I'll give you a second to think about it. Well, are they even different? Well, it's a little tricky. What do I mean by them being different? Clearly, when both of these rules that I've circled make sense, they're equal, right? Because tan is sine over cosine. But notice that those two rules accept a different set of inputs. So cosine on sine is a well-defined rule. It computes a real number as long as sine is not 0. And you can see in these vertical dotted lines here, these are the values at which sine is 0. 2 pi, pi, 0. So apart from those multiples of pi, the cotangent is defined. However, the tangent, if we were to go back to that graph over there, you could remind yourself, but of course tangent, which is sine over cosine, is not defined if cosine is 0. Cosine is 0 at pi on 2, for example. So that rule doesn't compute a real number at pi on 2, whereas this rule does. And obviously that's a bit fake, right? Somehow this rule really ought to be defined at pi on 2. There's nothing wrong with pi on 2. So that's why we prefer this. This is the definition of the cotangent rather than this. Now, apart from multiples of pi on 2, they're the same. So it doesn't really trip us up very often. But this is the distinction there. Okay. So we're going to talk about injectivity and surjectivity. And to do that, I need to introduce the idea of the image of a set under a function. And maybe the best way to do that is to start with this beautiful diagram here. So we're going to consider a function f with domain A and codomain B, and we're going to take S to be some subset. Could be the whole thing. And what we're going to do is imagine the following procedure. Pick any element x in S, and then hit it with f. And you'll end up with some element f of x in B. Now, do that for all the elements of S, and you're going to end up with some collection over here in B. And we call that collection f of S. It's the set of all the points which are the image of something in S, where by image I mean just apply f to it. You could think about shining a light. So you take a light, you shine it on an object, and there's an image of that object appearing on the wall, the shadow, right? That's kind of where this word image comes from. Okay, so that's the picture. Now let's have a look at the formal definition. This is just what I said, right? F of S is the set of all those things in B, which are the image of something in S. Or if you like, for every S in S, apply F to it, and then collect them all together, and you've got your set. So that is called the image of S under F. And if we do this for the entire domain, so S is equal to A, we get f of A. And f of A is called the range. Okay, so f of A is all those elements of B which occur as outputs of F. Okay. Now, you might be thinking to yourself, well, what's the difference between the range and the codomain? That's a good question. They might be the same, but they don't have to be. So the range is all the things that actually occur as outputs of F. The codomain is just some set which contains all the possible outputs, but maybe it's bigger. Why do we ever care about the codomain? Why not just use the range? Well, I'll come back to that in a minute. For now, we'll just roll with it. Okay, so let's take a look at this example. Use the graph, Luke. Yeah, all right, I'll do my best. Okay, there's our graph. Let's find the image of 0, 1. Well, what does that mean? That means that I take from here to here, inclusive, and I think about feeding all those inputs into my function. Well, in terms of the graph, feeding an input means take that element and go up to where you hit the graph and take the corresponding element of B, right? So if I do that for all the inputs between 0 and 1, what do I get? Well, 0 maps to 0, and then this goes all the way up to B, and I get everything in between. So this here is going to be the interval 0, B. Okay. What about minus infinity to minus 1? So that is, I take every input up to here, not including there, though, right? So let me put an open circle, right? Because this is a round bracket here. And if I feed all these inputs into my function, that is, send them up to the graph, well, it looks like it asymptotes to infinity. I guess that's what that means, right? Assuming the graph monotonically approaches infinity on the left, right? So we're supposed to assume that it just goes up to infinity there. So I'm going to get arbitrarily large values by going far enough to the left. Okay, so I've got all infinitely large, I've got all values that are large, and 1, or minus 1 rather, maps to 0. I'm not going to get 0 in my image, but I'm going to get everything that's bigger. So this looks like it is 0 to infinity. Minus 1 to 2, okay, including the endpoints. So minus 1 all the way up to 2. So I've got to imagine, well, let me just draw it in black, the curve that's part of that. And then I'm going to squish that onto the y-axis. So the highest it goes is B, and I get everything down to here. So that is A to B. Okay, one more. Range of F. Okay, so that means I take all the inputs. Now, if I go over that way to the left, I'm going to get all the numbers that are large. So I'm going to get up to infinity. I can't get anything lower than this, right? This is the lowest it goes. But I get everything above there. I don't actually care what's happening over there, right? I mean, I just need to know that it can't go down again, right? And that's what that says. So it seems like that is A up to infinity. The range of F is A inclusive up to infinity. All right. So there's 3 important properties of functions that we're going to discuss. The first one is injectivity, and then we're going to talk about surjectivity and bijectivity. Now, there are 2 equivalent presentations of injectivity here. So the first one says that a function is injective if whenever you feed in 2 inputs, A1 and A2, if they end up being equal, which is what this says, then they must have been equal to start with. And A1 must have been equal to A2. My experience is people sometimes find this a little hard to wrap their heads around. So maybe, if you like, start with the second condition, which says that if you start with 2 distinct inputs, which is what you probably mean when you say 2 inputs, right? So a mathematician, when they say take two elements of the set allows for the possibility that actually they're the same element, which maybe seems a little strange, but that's how we speak. So take two inputs, and they're different. A1 is not equal to A2. Then the outputs are different. So if you like, that means that F preserves distinctions. Two distinct inputs become two distinct outputs. That's called injectivity, or being one-to-one. Okay, and as you can see in this picture, there are three elements, distinct. I mean, the dots are in different places, and they map to three distinct elements over there. So if I was to draw something that's not injective, hopefully you can imagine it before I draw it. Not injective would be a picture that has, say, two distinct inputs and maps them to the same output. And you would say this is many to one, for the obvious reason. And so by contrast, this is one-to-one. All right, so an important class of injective functions are those that are monotone. So a monotone function is a function that's either always increasing or always decreasing. Now, just to be clear, if you have a function that's increasing in some places and decreasing in other places, that's definitely not monotone. It's not that everywhere it's one or the other. It's that it's either always increasing or always decreasing. Okay. Now, if A and B are subsets of R, then we can use the behavior of the inequalities in R to prove that if a function is monotone, then it's injective. And I'll just quickly sketch the proof here. So proof. Well, suppose it's monotone. And suppose you had two distinct, let me say, just in brackets, e.g. if f is increasing, okay, maybe you can think of the proof before I give it. If f is increasing and a1 is different to a2, either a1 is less than a2, and then I'll have f of a1 less than f of a2, right? Because it's increasing, or a1 is greater than a2, and then f of a1 is greater than f of a2. And in either case, f of a1 is not equal to f of a2. And the same argument works if f is decreasing. Okay? So let's prove that the logarithm function is injective. Now, if you look at the picture over there, injectivity corresponds to the fact that a horizontal line only passes through the graph once. You might remember the horizontal line test. So what's behind the horizontal line test? Well, the idea is that if this horizontal line were to hit the graph in two places, then that would be a value A, and suppose it happened to hit the graph somewhere else. It doesn't, of course, but if it were to hit the graph here as well, then you would have the heights being the same, and therefore f of A equals f of B. So hopefully you see the connection between the horizontal line test and injectivity. I'm not going to argue using the diagram. I'm going to prove it. So prove that this function is injective. And what we're going to use is using that the logarithm is increasing. Hopefully you see it's just the argument I already gave, right? It's just a concrete instance of it. Okay, so suppose A1 is not equal to A2, then either A1 is less than A2, then the logarithm of A1 is less than the logarithm of A2, or A1 is greater than A2, and then the logarithm, which is order preserving, right? I mean, increasing is the same as order preserving. So log A1 is greater than log A2. In either case, the outputs are not equal. Which is what we need. Okay, so here's a function, f of x equals x squared, which is not injective. Why? Well, by what I just said, right? We could think about this as a failure of the horizontal line test. If we want, let's draw a horizontal line. Here, it hits the graph in two places. What does that mean? So is it injective? No. Why? Well, because f of minus 1 is equal to f of 1. The graph has 2 points of height 1. Okay, what are the largest intervals on which f is injective? Now, this is an interesting point, which is to do with why we're introducing or emphasizing domains in the first place, right? So notice something, namely that if I is an interval, then let's call it f sub I. The same rule, but a different domain. Okay, so still x squared. We just change the domain to the interval I. This is a function. Okay, it's a valid function. Well, the point is that injectivity is a property of a function, not a property of a rule. Okay, you may not be used to distinguishing between functions and rules, as we discussed earlier. But what does the definition of injectivity say? Well, if we go back over and take a look, yeah, I guess it's implicit here, right? That A1 and A2 are in A. And similarly here. Right, the condition says that for all pairs A1 and A2 in A, something, something, something. So it's got to do with A. So it's a property of F, the rule, of course, but also of A. B isn't really very important. So if we come back over here and look at this new function, which is defined on the interval I, that could be injective, even though F isn't. And that's obvious in the diagram, right? So, because obviously I can restrict the domain, that is, restrict the x-axis, and get something which is injective. So if I, for example, is 0 to infinity, fi, the function, is injective, even though f is not. And similarly, I can do the same on the left-hand side. Okay, f at I is injective. Now it's interesting to note that if I were to take this interval and add even a small piece that went over here, right? If I were to add to the positive real numbers and 0 a small chunk that lives in the negative real numbers, that is, if I were to consider the interval I, which has, say, and consider this interval from minus 1 on 100 to infinity. Well, fi is not injective on that interval because you can draw a horizontal line very close to the axis and hit 2 points. Right? So if I include any negative numbers at all in my interval, it'll fail to be injective. And similarly, if I increase this I, which has the negative real numbers in it, if I extend it out to the right by any amount, that'll fail to be injective. So those two intervals are maximal. And that's what the question is getting at. It says largest, but that suggests like a measure of size. That's not really intended. It just means maximal, that is, cannot be expanded. Okay, so now we're going to finish off with a calculation, which is actually proving that some function is injective. So let's take a look. So how do we prove that a function is injective? Well, there's two kind of definitions you can use, right? One says that distinct inputs become distinct outputs, and the other, which is the one I'm going to use here, says that if you take two elements of the domain and they're mapped to the same thing, then they must have been the same to start with. And this is pretty convenient for proofs, because what you do is you start the proof by saying, suppose gx is equal to gy, blah, blah, blah. You do some stuff, and you end up with, therefore, x equals y. So you're done. Okay, so let me fill in the blah, blah, blah. What does that mean? Well, we just read the formula. Right? 2x minus 7 on 1 minus x equals 2y minus 7 on 1 minus y. So just multiplying the 1 minus y to the left and the 1 minus x to the right, we get 1 minus y, 2x minus 7 is equal to 1 minus x, 2y minus 7, and we'll just expand it out. So we get 2x minus 7 minus 2xy plus 7y is equal to 2y minus 7 minus 2xy plus 7x. Now, there's cancellations. The 2xy's cancel. The minus 7's cancel. I guess that's it. So we get 2x plus 7y is equal to 2y plus 7x. And clearly, subtracting x to the right and subtracting the 2y from the left-hand side, I get 5x equals. So thus 5x equals 5y. So x equals y. And I've now proven this, which is injectivity. So I can conclude, hence, G is injective. And that's all there is to it. All right. So next lecture, we're going to talk about surjectivity and bijectivity. But ta-ta for now.